Okay, so yeah, welcome back, and this is the second lecture by this.
Yeah, maybe I should start by saying if you have at some point if you have question about the previous lecture, I can also take that. Okay, even if I'm moving, but the topic slightly fine. So today I try to reach periodic waves. I'm not sure to go there. See. So what I mean by periodic wave is something that is periodic in space, and a wave is just that it's moving at a fixed velocity. That's the dynamics. I want to explain that. Yeah, I can also add that I will not discuss modulation system. This is part of the summary of the course, but clearly I will not do that. So if you are interested by this, I can also explain that. But before going to periodic waves, it turns out that the analysis near periodic object is very close to the analysis near constant solution. So I will start by just reviewing how to do constant stability. So that's near constant stability. Say a few words about multiplication operators. So in spectral theory, or that is the one I have in mind, there are two prototypes of operators. The finite dimension, that you know, by matrices and so on, and then multiplication operators. So I will explain multiplication operators, and I will also explain why that matter. So, I'm taking just the sigma finite measure space. Okay, and then some scalar function measurable. Now I'd like to look at say LP finite. And when my multiplication operator is just a given multiplication, the domain is what you expect. Okay. So I cannot make anything simpler than that. I just and it is a generalization of diagonal matrices. Okay, so it's a kind of when you think about diagonal in infinite dimension, you think about the multiplication operator. So it could be not completely obvious at first, but because it works. If I have a diagonal matrix, where is the n? But the thing you should do is, if you have a vector on CD, you think about this vector as being a function over the integral between 1 and g, that to each number associate the coordinate, and then the multiplication function is just you multiply by the j part by a the matrix. So that's how to see this as a generalization of diagonal matrices. And so let's do a few comments. So it's a good operator, meaning it's density defined, it's closed. And you can compute the spectrum in a very easy way. These effects. And another thing. Diagonal, so you know what should be the inverse should be just divided by the quantity. The question is, does it make something that is continuous in LP? But that's the same as the invert. But this set is called the essential range. And so you should think this as being in good cases, this would be just the value of 10. But you have the right to just forget about things that are zero measure. So let me also point out that if the level sets of n are of measure 0, then there's no eigenvalue. There's no eigenvalue at all in the frame. So this is of course not the case for diagonal matrices. That's the case to. Okay, if you go to non-ordinal things, and then you to think about the case where things are continuous and nothing as a positive measure, then and I'm showing you this mostly because that's the case that you should have in mind for scalar constant sufficient. I mean, it's and something that is like what I mean by this is by definition that it's given in Fourier by multiplication by now that is Fourier. On I want to use that Fourier with isometry so that I could write directly all of those properties on the Fourier set. So this is typically the message here is that Fourier is diagonalizing in a way constant coefficient operator and diagonalizing in the sense that it becomes just a multiplication by its scalar function. So in particular, you can write directly the spectrum from what I said before right here and get everything you want. Yes, then once the operator is diagonal, the functional calculus is trivial. It's exactly as for matrices. Everything is very nice. It's already a little bit worse if you remove the scalar part. So if you remove the scalar part, you're not quite a multiplication operator. You're acting, you're diagonalizing the dx part, but you still have something that is a matrix. So it's more like you have finite dimension parameterized by something. Then something that helps you in this case is to know how to focus on some part of the finite dimension. Okay, so like you have a matrix, but most of the eigenvalues they remain separated, and you want to be able to analyze them one by one, or maybe two by two, or so on. And for this, you need to be able to zoom on some part of the spectrum. And this is something I'd like to explain now. It's motivated by the vector case. I don't know you. Vectorial constant position. You know how to do perturbation theory. What do I want to do exactly? I have some family of things. Okay, let's say matrices. And epsilon, you could think about epsilon being the Fourier parameter. And there is no zero element of the vector. Epsilon equals 0. And you'd like to understand what happens for A epsilon, but only the part that is near lambda 0. Okay, you want to be able to forget about the other parts. So we more or less start to see how to do this kind of thing. The first thing you should do is introduce a projector, okay, using some contour. And then I have a projector, a finite dimension here. I could just write it as a sum of rank 1 projector, because I've done it yesterday, or rank 1, but sum. So for this, I need a kind of basis. This is the basis for the image, but if I want to make the projectors, I also need to get the dual basis. Like yesterday, we have a d over dt of u bar 0, and we introduce some L0 to make the projector, so I'm doing the same thing here. By U, I need but I can use this as coordinates for the but the scalar product things. I've done this for 1 point yesterday. Now I'm computing I have mentioned. And this is the situation I start with at epsilon equals 0. I'd like to understand how to extend this in epsilon. When m equals 1, this is very easy. I want nothing to say, just inversion function variability. So, then the question is as long as diagram, you can define then maybe the same formula for the projector. The only thing that you know is the projecting inside of them. So now you don't know what is the projector, but it's actually what you want to understand. You can fix the gamma, you will fix the resultant in the formula for the projector. Everything is smooth as long as the thing that appears in the contour remains invertible. It's exactly the assumption I made, but the fundamental thing in the end. Okay, so then you have a good projector. Very smooth. Well, the question is, how can you use it to extend the basis? We need to keep get coordinates. Why do I care about coordinates? It's actually because once I have coordinates, I will be able to form a matrix of size n. I'm studying a matrix of size n. Now, if I make the spectrum implies because the spectrum of the bank by channel. Corresponding to taking coordinates. Base. Once you have this, you're back to okay, so this is useful even for when A epsilon is already a matrix, because then you're doing that from the matrix that has a multiplicity of eigenvalues. So it's mean that the eigenvalues are either simple or C2, then you mean that you just have to study 2 by 2 matrices or 1 by 1. And then you have huge reduction. I will not explain how to the extension can plenty of course. It's not completely perfect, and there are many flaws. I'd like to insist on that everything is completely smooth here. But these are the bases are not forming the basis of eigenvalues. These are not eigenvalues. Spanning the whole you're also going for the sum of the eigenspaces. There are eigenspaces, but not separately asking for each eigenvalue to have an eigenvector. More or less, I'm reduced the problem to do the scalar. Exactly the problem. So I just want to explain how to do the scalar analysis. Or I will do it on a trivial example just for practice. No. Start with the heat kernel bounds, but I don't want to do it by introducing using that I can explicitly get the heat kernel. I want to show you how to do the proofs and make some comments about that. I'm putting myself some constraints to see how far I can go. Right? So I'm okay with using mostly order inequalities and Young inequality, but and also say it's a linear allow to use prime for me is always the lower index. The back units prime over the back units. So this I mean okay, this is almost L2 it's just Parseval, I've already mentioned. And L1 in infinity just comes from the formula for Storm. And then you have this interpolation give you all the rest. So I'd like to see what I can get from that. I'm showing you this just to say that there is an easy case. The easy case is also more robust, right? Because it uses less things. So this is the thing that I would be able to extend very easily to more complicated cases. What is the easy case? It's the case where we can do everything just with this. That's the case where you want to do this, then and there are constraints. Like I'd like to study LQ by going to Fourier, then But then I need Q to be larger than 2, so if I want to control something with that. And then I'd like to finish by the LP norm. This means that I can control something only if it's less than 2. So let's do that. Let's see that. Okay, so I'm using that Fourier diagonalizes. I can solve directly the operator. I get the exponential multiplication and so on. And I want to control the L2 norm. I start by going to L2 prime. It's possible because Q is larger than 2. Then in the end, I want to control this guy by U0 in LP. And this means that I can control this thing only by LP prime for him. That, so then I need to put this guy in LP prime, so that tells me where I should put the rest. Order inequality should be the external R prime values. Then and essentially I'm done. Just need to compute that, but I don't need an exact computation. I just need to know how it equals in T. So I will just do up to some constant. I'll write it with R. And just coming from the change of line, step 9 was scroll and see. We get that something finite and some right over the coefficient. You use almost nothing. Okay, like, it's very low tech. Then what I will do is introduce the curve. The multiplication in Fourier, so it's a convolution in space. But I don't want to use an explicit formulas. Formula for the input, but I only want to use the fact that it's Fourier minus 1 of the thing by which I multiply. Now I use strong inequality, so the goal is to get a bound. Yeah. Want it for any R. What I already have for free is the infinity bound or the L2 bound. Okay, anything above L2, I can get it by the same argument as before. So the goal is really to get down L2. But using only Fourier analysis. So more or less the only thing you can do is to say, okay, if I need to go below L2, I need to gain in localization. To gain on localization, I can gain some moments. And then this becomes some derivative on the Fourier side. So you can do that. Then after some computation, mostly a change of variable as before. Get that like square root of t and this is mostly a change of variable. So each time you differentiate something that is a function of c square root of t, you pay a square root of t. That's why you get something here that's a bit different. Yeah, this is exactly what we get. But I want to use this to get some integrability. So I will just combine this with the identity bound I will before. One by bound by. So it's just I forget all this is a infinity bound. I forget about this is the bound with some power. Now, once you are here, it's fine. Okay, you just have to integrate and do change of value. That gives you effect. The dual one to the Fourier side. Yes. Change homogeneity by going from space to Fourier. I'm not claiming that this is much harder. I'm just saying that it uses more things. Like typically, it uses the fact that you have a convolution structure for the multiplication operator. So this is one thing. And the other thing is that it uses regularity on the Fourier side. Because I'm differentiating over respect to C. Okay, so the first bound, there is no derivative in C. And then, okay, even if I have very bad spectral properties, this could be okay. Okay. For the second bound, I need some good spectral properties. And it's not because I'm bad at doing bounds. Okay, it's really true. Like if you have a bad spectral regularity, then in a way you will lose localization. And sometimes this is good because losing localization could be associated with a decay by dispersion. The failure of regularity in XC could be the sign that you get some kind of dispersion and you could use it to get better random pattern. I will not show you this, but okay, this is something fundamental. Like, so it's not. And also, see that as much as it's sufficient, I prefer to use this one. Okay? At least in complicated problems where you have to try to get the most efficient rules. Now you do another practice. So an example of stability of constants. More. I want to prove that I can get the decay but at the linear level. There are many ways to do that. Okay, I will just want to show you one that I think is quite robust. Note that the decay is not very strong. Okay? If you just look at infinity, it's like 1 over square root of t. So it's far from being integrable, for instance. Okay, so I need the structure to help. If you think about Grandval kind of bounds, more or less the integrability in time is in principle the threshold. Yeah, you use that the dx is bringing you some kind of 1 over square root of t. So then it's like 1 over t is integrable. Almost. So let's do that. I could have done this before. The linearization is like fit equations we had before, and the generator is like dx squared. So from what I said before, the spectrum is the image of c2 minus I squared. So c2 minus c squared, the spectrum is just a negative. Where I x minus infinity. So there's no spectral depth, you cannot expect anything exponential. So we are just proving an algebraic thing because of that. We're going to I can I excluded so far infinity from my examples when I was using LP. There was a reason for that. It's just because you cannot really define a good generator on infinity. There's actually a theorem telling you that only the bounded operator generates semigroups on infinity, and it's due to the fact that you need some kind of densely defined domain and the cells all the time. So the price to pay is that when you read an evolution, it's not continuous time. It's just after that phase. Don't get continuity name. And then the translation is not like continuity. You can get continuity if you are playing the topology that you mix down. Another way is to, of course, replace infinity by a delta space. Yeah, yes. Voilà. Énorme, une cause de decay, and I want to do a super decay. Based on the not quite saying what down, the super thing is that you will certainly the response on the one building on the values. You will touch some like if you expect the right hand side and try to get them back with an improved constant somewhere. So the thing you need to know is that you understand what that comes for this alpha. Time evolution. Also, machines by doing a generalizable. And I would get like one of the I would have to my like getting of estimate, and then that result that the integral is finite. But then when you do that, you get important complications. So you need this to be integral. Okay. The same thing with the care of the key, and then the constraint would be on the time. The issue would be the same, but you can guess. Let's try this. Say I want to form I only need okay, I've written a soup over P, but I only need L1 and infinity because I can get the rest by interpolation. So let's do first L1. So if L1 does not such decay, so the risk of the both one are there are also not much choice. The estimates the linear estimate adjusted weight. You don't have many. I mean, if you say Q upon 1, you need to P equal 1. So there's no choice. The only choice you can make is to be to include some derivative in your norm, and then to convert the derivative not on that. So I get 2 minus S1 half from derivative, then I say L1 of the square. In the square, but one thing is infinity, and another one L1. little less. Be more careful about the fact that they should stay below this one. When I'm trying to lower as much as possible, and they are there, the reverse function percent. It just corresponds to the fact that here I'm using the value one infinity rate. Here I'm using the infinity and in the end, both are using the ground. One comment about the fact that it's actually critical, and like I get exactly the decay is there's no. This is a critical situation. The nonlinear terms they decay exactly as a linear amount. If I were going to higher dimension, I would be in a subcritical situation, and there would be room for losing things. Here, I cannot lose anything in this argument. Okay? In particular, I was needed to be careful about this because otherwise it's kind of loss. There's no room for that. It's that's our question. It's more than one. Yes, that's a no. Yeah, and actually for this equation, there's a many ways to. One is there's a trick to but it's actually in a way this equation is integrable. Okay, so the integrability is a Polar transform that brings you this to the heat equation. The linear constant coefficient they are integrable because of okay you can diagonalize them, and this is actually to a large extent what motivated the people that have invented integrability. This example is related to integrability and Lax pairs and things like that. This fact that this particular equation with a square, okay, exactly this one, the integrability is okay, but you cannot change anything in the equations. They are not much. So this one is it's integrable by Polar. So there are other ways to do that. And I can make another comment. So this transform was actually invented to do the vanishing viscosity limits. So if you put on epsilon here and you like to understand what is happening, the whole Rolf transform is scaled. So again, I'm doing this just as the simplest example where I can show you the general robust argument that I would use in other context. But as you see, I mean, this is quite robust. Okay, if I could do this plenty of equations, that's for no function. There's also some self-similar behavior that you think you can say with this equation.
Sorry, I do not understand your comment about integrability. Let's say the size, the fact that you know there's a restriction on the size.
No, I'm not saying that you can. Okay, so what is integrability? This is not a good example.
No. Yeah, I didn't want to.
But okay, so the toy problem or the toy situation for integrability is exactly concentrated in the Fourier. The time evolution is not trivial, so you go back by Fourier, Fourier, okay, situation that you say integrable. So the genomic vector is different. What is Fourier expecting? As in Fourier, that's good to think about this kind of argument where you don't need to know very well the intersecting to get into the information. I'm saying that for nonlinear solution, you have to do something like this. One way to do this, and this is the way to do here, is to find a transformation that brings you this to quantum coefficient equation. In this case, this is called one. And I'm saying that once you have a level of this equation, for linear equation, you don't have to go back.
Yeah, but let's say if you have a cubic term inside it.
No. I'm thinking like, okay, the miracle is that I cannot change anything.
Yeah,
I need a square.
But even with the cubic term, you wouldn't have a restriction. It's more.
Okay. No. Okay. I just said that there are many ways to see that you don't need a restriction here. And I don't want to go into but yeah. I think so.
If you use the dx out of use for essentially in an argument, yes, we know it's known that the equation goes up. Yeah, so it's not that we can be parallel.
No, that's true. But if you do a cubic term, then that's
Just use square.
right. And we need repeat what I said before. Like I'm aiming at one of square root of t. So it's not for me integral. I need some kind of integrability that I give up in the argument. And it's coming from that I did it's in factor that you don't need one more one of square root of t. Then I work on t, I can integrate it. I can remove it, then it's completely fake. So this situation is critical. You see that anything below is super critical, so there's no point to doing it. The linear equation is dominated by the nonlinear term. I'm trying to do a fixed form, so it's okay. It should be completely different. So more or less the picture you have in mind is okay, so critical, it should be easy. Critical, maybe you can manage, maybe not. And super critical, okay. But I'm giving this example mostly because I'm only interested in cases where there's a dx in factor, when it's in factor of everything. Interesting situation where things happen because of the non full structure, which is not some accident. So in the case I look at, if I have no dx in factor of the u square, I think that I don't have also a dx. I get some spectral gap or things like that. Things would be complicated. Okay. Now I'd like to go to periodic things and try to get essentially the same things. And I need something to replace the Fourier transform. Right, cross common is Fourier does not diagonalize periodic position. Whereas when I will linearize about something that is periodic, I will get something that is periodic position. So I need something to replace Fourier. So it's not writing the inverse formula. I'll do 1D and period 1. It's X, 1. So Fourier is writing anyone as a sum of objects that are just actually trigonometric monomials, like pure exponentials. Here I'm writing anyone as a sum of this kind of objects. So okay, what is exactly the structure of the subjects? I think a good way to think about that is to look at it and see what happened when I had one. to X. I just translate by one period, and I'd like to see what happens. So for this guy, nothing happens. It's one period. Okay, if I translate, nothing happens. So what happens here is that it's coming from here. So the full thing is just multiplied by PIC. Okay. This is something of modulus 1. So okay, that's name. So this EIC is called a Floquet multiplier. XT is a Floquet exponent. Okay, the full block is called block wave, and so okay, that's a double name. Where does it come from? You already know Fourier, it's quite easy. You just take your Fourier formula and you split the integral of R as a sum of integrals minus pi pi. You just put them together. That is the formula. You get the part of the Fourier that is between minus pi and pi factor, and the integral part you put it together with that. It's not R that this is coming, what is coming from Fourier. And it also looks like an inverse Fourier series. But you can see, I mean, I'm summing periodic trigonometric monomials with some coefficients. So if I know what, okay, but this is the Fourier series of someone, then I will get, I will just recognize Fourier series. Okay. You can also do this computation. You can compute that this is the, I mean, it depends on my convention. A bunch about that, and so and check that it is our coefficient associated with the periodization of someone. So again, to check that, that's essentially the same game. You write this as an integral over R, you get this parts of size 1, and you group together the parts to make appear something that is like this. Okay, so this is indeed periodic. X, if you add 1, the formulas that change. And then, okay, this also means that I have another formula for that because when once I recognize that this is the Fourier coefficient of this guy, I think that this thing is just this guy. This equality here has a name. It's called the Western formula. The proof is essentially what just this remark, but this is the Fourier coefficient of this. Yes. Yeah. Okay. So that's a good question. So if you, the way to prove that is to begin with this case, with a U that decays at infinity. But then you can extend it then you can extend it by duality and density as you do for Fourier. Okay, the discussion is exactly as for Fourier. If you want to start establishing the equalities, you need to get some kind of regularity. Then you can see what are in which case you are continuous. You can extend by density and then even by duality. But exactly as for Fourier. Okay, I will start with that. I will give some continuity properties for B and all. And that you already see that for in L2, it's slightly clear that it's like you have both some kind of combination of Fourier transform and Fourier series that are together. This gives you some kind of isometric properties. one more comment again. Give about that is that I will linearize something that is periodic, but I'd like to look at the dynamics on R. So that's why I care about diagonalizing constant coefficient operator, but for functions that are living on the whole space. So otherwise, if I was just choosing to work on a torus, I would use just Fourier series. This is not what I want to do. I want to work on R, but I have periodic coefficient. One to run on two. Not even like mostly for anything. I have one that's constant for which one. I forgot to say at some point that what I said about the continued property of Fourier is called absorption estimate. So I also add absorption estimate for this one. I have L2, L2, and I just need to look at P equal 1. Okay, and then I could do interpolation. But unlike Fourier, block transform and inverse block transform, they don't have the same structure. And then that's also, as for Fourier, that's easy to do on the transform. Well, for instance, if I want to check that yeah, I forgot to count this one. Okay, so for instance, you can check here that if you control this infinity in X and 1 in C, then okay, just indirectly at the integral, if you want to set the modulus 1, you can control this in infinity. But this is one. Okay, once you have this in L2, L2, then you get your. And to control the inverse, that really easier to use this formula. Okay, just take this. I know that, but once you have this, you can actually reproduce the proofs I've shown you about the heat kernel. The other thing I need to check is how does it commute with standard operation? So I motivated the introduction of that to check that I could diagonalize periodic coefficient of that. And of course, if you want the TX part of the TX part is already diagonalized by Fourier. That's the multiplication by something that is periodic that should become diagonal. Okay, so C by T is just X C by T. Okay. If I was doing Fourier, there would be a convolution mixing all the equations. Here there's no C by C. Okay, what you gain on the multiplication, you lose on the derivative side. It's still diagonal, but it's less simple. Formulas, once you know that it's you get something that is one-to-one, you just have to act on this formula and see what happens. Okay, so when you multiply by A of X, you can put it directly here. This is something that is one periodic, so it should be the block transform. This is fine. Okay, when you add with the X, this is the same. The dx goes there, except when it hits the exponential, and then it's dx plus X. Okay, everything is very simple. You can also see that if you have something that is low frequency, then it's also already written in Fourier as an integral between minus pi and pi. Something that is constant. So this means that you can directly read the block transform as being a Fourier. So I write it. Low frequency. That this means that the support of the Fourier transform to minus pi. Then I'm not too precise about that. So really like the same kind of problem. I think that the calculation of the consequence of it is that if you just apply the block, it's a and one value. Then you completely separate. You should think of it as a product that is like a cartoon of what is the modulation. You have something very deep, you move slowly. So the simplest way to do that is to do exactly this. Take a variation and multiply by something slow. But you'd like to be able to recover, for instance, the modulation part, and the part where the amplitude that you know. And a simple way to do that is you apply the transform. You will raise the X part, and then you get the only one. It is used to be everywhere in the field. So we announce that straight head one the action is blocked by the what you get is that you have something that was acting on R, function on R, like you have something that's now acting in parallel function. All the action is that is given the formal ground treatments and then like something like this, then LC with explain whatever the place and the ground next reference. So this, I mean, I'm just summarizing the discussion about this is true for multiplication. This is true for derivative. I think that is a combination of multiplication and derivation and differentiation. It's like this. Okay, when do we gain something about going to derivative? Do you gain something if your data is gained? Then the domain. Okay. The domain contains the derivative domain contains control derivative, and if you control derivative on the doors, then when you say about compact operator, then the spectrum is much simpler. Okay? For compact operator, you know that the spectrum is made of eigenvalues of time density separated. So it's not exactly like Fourier was able to bring you from acting on R to being a finite dimension parameterized. That's what we said before. Yeah, you're not back to finite dimension, but almost like okay, you are back to discrete eigenvalues of finite multiplicity. Okay, there are infinitely many of them, but it's discrete. Can check for acting on L2. You don't need much to prove that. Like beyond what you were expecting, that the spectrum of your operator on R is now reduced to eigenvalues that are discrete, parameterized by C, then move with C. Okay, if you have a perturbation theory, you can follow them, and so on. So in this part, you can if you comment. So if I do C equals 0, then the Floquet multiplier is 1, which means that I'm looking, I think, at our period center. So inside the spectrum, there is a part that I will get if I were a person on the torus. Find that C equals 0. And when you do Xi non-zero but small, arbitrary small, there's actually a name for that. It's called Seidel perturbation. Maybe you already heard about Seidel instability. It's an instability that comes from with Xi that is very close to 0, but non-zero. Okay? And a object that is almost coperiod. Not exactly, but it's not moving much after one time. What I want to say about maybe you've noticed I say nothing about convolution. More or less, I lost also with convolution properties. Say begin the discussion of very equals. Take one example. Well, Barbaric system of conservation law. That's a bit like Berger's case I've shown you before. So, but it's a system, and the solution, the background solution I want to look at is something. That's a traveling wave, okay? Something that doesn't, I mean, the evolution is just translation in space at a fixed speed. So I can write it. Okay, so in time, it's just translating x with some speed. And as k period to be 1. So the k bar here is just to get period to 1. I need to do things like that because I'd like to compare periodic objects in the end. So I need to put them all together on the same scale. Before linearizing is convenient. First, I need to go to the moving frame to make my wave stationary. Then it's convenient for me to scale also per period to be 1. Then the equation. Okay, yeah, sure. I will write time and then I will drop the time squared. In the linear operator, I'm interested in this. Right here. Right. I'd like to say a few things about actually the structure of waves. Why? For essentially the same reason as yesterday. It's because the fact that my wave is not isolated will have some impact on the kind of spectrum I can get for the order. If you remember yesterday, like the fact that the periodic solution were isolated, where they were created some eigenvalues. Okay, so this is the same game here. And I need to first understand what it is. That translation in terms of playing a role that is a this solution that is saying that translating in space. I can start with the symbol parameter. As yesterday. I don't know if it's translate. Yeah, it's more than that. The first thing is that I just translate everything. Thanks. I'm solving the equation. Change nothing, but this already gives you something as yesterday. If you just plug that this is a solution for any phi of the profile equation, and then you differentiate with respect to phi at phi equals 0, you get something. Okay, so first, when I differentiate at phi equals 0, I get something that is periodic. So then it's you should not think about this as being something on which L acts. It's L0 that is acting on it because you're acting on something periodic, so it's C equals 0. So if you differentiate, get the L0, you are 0. But remember that again, 0 is in the spectrum, that is the spectrum because it's L0 as a kernel, and the union of C of the spectrum of LC is the spectrum. So in particular, in this case, it cannot really be isolated because once you have 0 for L0, for LC, you will get nearby eigenvalues. So it was once you have at least a curve that is going to be touching 0. But there is more than that. Wow. Yeah. Then there is the inside here. You need an assumption somehow. Generally, by this. How do you see that? It's pretty easy to see. You just look at which equation we need to satisfy. Put this into the equation. You look at what should be the equation for the profile, and you are trying to analyze your superstructure. And this is an ODE because of this ODE, and it comes to because of the conservative structure, it comes with dx in front. So you can integrate once. First, this will introduce some constant of integration. Then you get an equation that is like this. And you have the equation to is the equation. The only thing you want to ensure is that it's periodic after periodic one. You have the freedom to choose the initial datum somewhere. You choose the initial datum, you solve over period one, and then you set as an equation the fact that it should match that datum you started with. So for this, you have essentially these three parameters, the equations. That's something to check. That tells you that you should be able to do that for any choice of the parameter. You look at the parameter. So the down to what? It's getting you exactly these numbers. So I did not say what should be M. The impact of K is complicated because K is everywhere in the equation. The impact of N is very simple, and N is nowhere in the equation. So if I differentiate with respect to N for the equation, and we get very simple, with the research of some of the power parameters. Is that's one of them. This is depends on the profile and the speed. And then you will get the derivative of the speed also. We already knew that. So this is a kind of Jordan block structure. So you have an element of the kernel, and for the other ones, and they are sent to some multiple of element of the kernel. Okay, that thing I'd like to say is that this is for the direct operator, but as we've seen, we also need to understand what happens for the adjoint, okay, in particular to build the projector on the slope. And for the adjoint, some of the things are very simple. Everything is conservative. The adjoint you just get by doing integration by part. This means that the adjoint, it starts with the dx, then it does other things. So any constant function is in the kernel of the adjoint. The definition would say that if you see an element of the kernel of the adjoint, you can actually force duality with respect to parameters. Like that, and then conclude. Yeah, when you do a constant on U prime, it's always zero. So this guy is already orthogonal to all the constants. Because that's the derivative of something very big. So that's the derivative of constant is zero. So if you want to force some duality, it can only come from the other. Then you can decide that you parameterize n in such a way that you get good properties that you do constant. The canonical basis of RB and I can force that. Okay. Play a role when we start to use some basis for perturbation. Okay, I've seen before. We need to choose the basis at equals 0, then do some perturbation. We'll do this tomorrow. Because tomorrow what I will do is a stateless stability theorem you can call. And then okay, give some insight about what do you do with the Jordan block, what can you get. So I will only show you this, okay, how to deal with the Jordan block, because the rest of the arguments, they are essentially the same as in the constant coefficient case. Okay, you are doing the linear estimates or actually a mix of what we've seen for constant coefficient and what we've seen for periodic coordinates. But the two proofs together, you get the elements for a combined. Okay, I'll explain this tomorrow. Let me just maybe tease the fact that the stability theorem, we will see something that we've already seen in my first lecture, and certainly also in the lectures of Thierry Gallet, the fact that position matter a lot. Okay, so you have to capture very close. Okay, you have to be very careful about synchronizing position for doing any comparison. Okay, you have to correct this very precisely. This is like the dominant behavior is missing the right position. If you are trying to compare two things that are identical but at different positions, the size is very huge. Okay? You have to first do the synchronization very accurately. And in this case, because I have something that is periodic, I have infinitely many position fits. So I will need to do like the phase shift, as in the OD case, but depending on time and scale. Okay, we'll see this tomorrow. So, yeah.
Okay, so time for question.
No, no, because the K derivative is not directly related to yes. So we have everything we need. We will see the role of K tomorrow, okay, but it's more complicated. So in a way, they're differentiated. Okay, it's at scale K, but in a way, differentiated with respect to K corresponds to moving the period. And then it's not at fixed shock zero. It's related to what you do when you move. Okay, so derivative with respect to K is a bit like the differentiated with respect to X.
Okay. So if there are no more questions, get the Luis again. Yeah, there's the source, and just let's say, I want to say, I don't know if you know, but there would be a conflict right now.